Hello, I'm Philip Zucker. This is EGraphs and Automated Reasoning, looking back to look forward. This is a summary of my discoveries over the last year or so of interconnections between EGraphs and automated reasoning, analogies or exact correspondences that can hopefully be used to extend the expressivity of EGraphs to more applications. So today I'm going to talk about the idea of term simplification and term completion, and generally a survey of the rough areas of equational reasoning and automated reasoning. In particular, then I'm going to focus on demonstrating how the union find is an example of ground atomic completion. Then the next natural step, the thing we're actually interested in today, is how the EGraph is an instance of ground term completion, and then how that can be used to supply as an approach to give the EGraph the features of lambda terms, a notion of context, and a notion of integrated destructive rewriting, things that are desirable and useful from a modeling perspective or performance perspective for EGraphs. And then sort of a general thing to chew on during this talk is the idea that the thing that makes the EGraph so compelling is that it's used in more applied situations in compilers. And I think there's a lot of fertile territory in general for taking techniques from automated reasoning, and applying it to compilers. The EGraph is just one instance of this, but these other techniques can be applied in this way too. Something to chew on. So, in the beginning, there was simplification. Greedy term simplification, where you start with some term and you find patterns in it of things that aren't so good, like here, for example, a plus 0. You find that pattern inside your term, and then you replace it. You mutate your data structure, you mutate your tree, and you replace it with a better form of that pattern. For example, a, where we've fused away the adding 0, which was a useless operation. Now, greedy simplification is really good. It's very simple. People can come up with it. They don't need to go study with a monk on a mountain in order to discover greedy simplification. It just is a very natural occurrence to anybody who starts thinking about optimizing expressions inside compilers or inside database systems or something. In addition, it's fast. It's about as fast as you can be in regards to simplifying expressions. Just like you had one version of it and you smush it, smush it, smush it, smush it until you get a small version. Now, it's not perfect, however. There are some bad features of greedy simplification. There's rule interaction and the phase ordering problem, which you might also describe as a non-confluence, a breaking of confluence. And the issue here is that you can have two rewrite rules where the order in which you apply them changes the results you get in a particular way. Maybe if you apply one rule first, then you can no longer apply another rule that would get you to an even better position. And so we have a canonical example here from the EGraphs community of you want to take multiplying by 2 and turn that into a bit shift by 1. But you can also find a times b divided by b and just have a. You don't need to multiply or divide by b at all. And if you greedily take that left rule first, the right rule no longer matches. This is unfortunate. And it can be hard to sort of control this, especially in a larger project with many, many rules and many, many contributors sort of making new rewrite rules and things. Another issue that's maybe less serious pragmatically, but still an issue, is non-termination. A plus b goes to b plus a is obviously a non-terminating rewrite rule. I can just keep using that over and over and over and over, and I'm not making progress. And so you can just limit the number of iterations of term rewriting, and that will stop non-termination. But you are doing a lot of unnecessary work. And if you throw away that rule, maybe you're not able to unlock simplifications that you might want. And so, on this last point, incompleteness versus suboptimality of greedy simplification, that is sort of the other two problems are part of the reason why you might get suboptimality. But also just greediness doesn't always give you the best possible thing. You're taking these very local moves, but sometimes you need to go up a mountain, way up a mountain, in order to find a deeper valley on the other side. And greedy simplification isn't going to do that for you. Okay, so a solution that's getting popular in at least a research community to some of these problems is EGraphs. They're good, is the short version of it. They're graphical. They have a graphical interpretation, which is sort of crucial for their uptake because, again, people don't need to go study the monk on a mountain in order to understand what the eGraph is. They can see this diagram, and you can sort of explain what's going on there, and you can sort of get it. The picture is really crucial for the uptake of this thing. And it is relatively simple, a fairly simple set of ideas. Not quite as simple as greedy simplification, but pretty simple. They're also declarative-ish. They're more declarative than greedy rewriting. They have less of a phase ordering problem, or no phase ordering problem in a certain sense. And they're also operational-ish, which is both good and bad. There is still, you can choose which sort of rules to hammer on or not hammer on, and that may bring you to good regions of the search space much more quickly, or if you use a bad ordering of the rewrite rules you're going to apply to the eGraph, maybe you'll just run out of memory and not get to the place you want to get to. And they're also fast-ish. There's a readily available, highly optimized implementation, in particular egg in Rust, and it is pretty fast. It's not as fast as greedy rewriting, but it's another point on the trade-off curve. And there's many, many applications of eGraphs in compilers in particular. So we can go over here to the egg website. And you can see a list of some interesting applications here: linear algebra, hardware accelerators, database engines, CAD programs. And also I'll note this link to Google Scholar of a back reference search from the egg paper can get you more modern applications. This list isn't kept fully updated. And I also want to note that there's sort of two main usage modes that I see people using. There are more, but the two main usage modes people are using egg in, or eGraphs: the proving mode or the simplifying mode. And the proving mode is you give in term A and term B, and then the thing runs, and eventually returns a bool saying if it's proven them to be equal or not, or perhaps a proof of them being equal or not. But a different mode of usage is simplifying, where you give it an original term, and then the thing runs, and eventually you get a new term that's better in some sense. And so this first use case, proving, is sort of the main use case in the automated reasoning community. And the simplifying use case, although the same techniques can basically be applied in both situations, is less served by off-the-shelf automated reasoning solvers. So here is the canonical example eGraph pulled directly off that egg website. And what we have here is a starting term. A times 2 divided by 2 is a starting term over here. If you take that term and insert it into the eGraph, you have this. And to notice some crucial aspects of these diagrams, there's these dotted lines, which are called E-classes, and they can collect multiple things in them, things that are equal to each other. And there's E-nodes inside the E-classes. And note that unlike a typical term in which the children point down to other nodes, here the E-nodes, the child points to this dotted boundary, to the E-class, to an indirection. And this indirection is the thing that enables more sharing between equal terms. When you're traversing down the tree, you have a choice of many equal terms to choose from as you traverse down the tree. And in that way you get sort of compacted behavior and memory. So then what this example is showing is that there is this rewrite rule that if something A is multiplied by 2, we can just say that, oh, that should be a bit shift by 1. And if we assert both of those, this equality here, we get this resulting eGraph, where this bit shift is in the same E-class as this multiplication. So now up here, we have a choice of the division of A times 2 by 2, or the division of A shift 1 divided by 2. And so this is representing both of those things in superposition. But they are sharing, for example, this division node, which if you think about how you might do this in pure terms, it'd be difficult or impossible to share that division node. But then you can go another pathway, and you haven't fully committed to this as you would in a greedy rewriting system. And you can discover also that if you can reassociate A times 2 over 2 to A times 2 over 2, and then you can notice that this is something over something, and that's the same thing as 1. And then you can also notice a rewrite rule that A times 1 is equal to A. So if you do that sequence of things, you end up at this final eGraph. And this is a canonical representation of asserting all of these equalities. And it doesn't matter. During matching and rewriting, you would discover these equalities in some order. But the order you assert them to the E-graph doesn't matter. You always end up at this canonical E-graph, regardless of the order you discover these equations. And then now you have the ability to notice that this term up here, this division node, is in the same E-class as just A by itself. And that is indeed the simplest form under the rules we've discovered of simplifying A times 2 over 2 is the same thing as A. Okay? But there are other refinements you can take to greedy simplification, other approaches to equational reasoning in the automated reasoning community. And I'm going to go over a couple highlights, a couple big areas, big cuts you can take of this design space. The first is paramodulation, which came about roughly in the 60s. And the idea there is more or less go breadth first with your equational search. Instead of taking a term and mutating it, destroying it in place, instead you can apply a rewrite rule or an equation and then make a entirely new copy over here. And then keep finding new ways of applying equations, make a copy over here, over here. And eventually you have this growing set of equal terms. And that is a complete method. You will eventually get out of the valley and go up the mountain, but it's quite inefficient. Also note that, as described, it's quite inefficient, but there's data structure optimizations you can take on it, or other techniques, such as the ones below, to avoid so much breadth firstness. In addition, from the very beginning, this has been conditional, that paramodulation comes as a resolution theorem community, theorem proving community, which is discussing clauses, which is a giant OR. A clause is an OR of many atoms, which are negated or positive, logical atoms. So when you extend this to paramodulation, now it's an OR of multiple choices of what things are equals. You're allowed to have that flexibility if you want it. And so from the get-go, paramodulation has been conditional or contextual, maybe one might describe that as. Completion came about roughly in the 70s. And the idea there is to take a system of equations and turn it into a good rewrite rule system. So once you have a good rewrite rule system, you can greedily apply greedy term rewriting, term simplification, and you'll be guaranteed to always get to a canonical best result. And so completion in particular takes this equational system and turns it into a rewrite system, if it succeeds, that is terminating and confluent. Also, completion has a notion of removing redundancy from your system of equations or from your system of rewrite rules. And it has a methodology and of going about that. And then finally, superposition, which came out roughly in the 90s, I like to think of as roughly a combo of these two ideas. It's limiting the equational search using the notion of a term order, which is also an essential part of completion. Term order is more or less a way of describing what terms are bigger than other terms. And you want to orient your equations such that they are making progress in some way and will eventually reach a final goal. Superposition sort of integrates this into paramodulation while retaining completeness, and also has the ability to describe conditional situations or contextual rewrite rules. Okay, so going more into completion a little bit, completion makes equations into good rules, ones that are terminating and confluent. And when you say confluent, you could think of this as the no phase ordering problem. It doesn't matter particularly what order you apply your rewrite rules in. You don't lose the ability to eventually find that good term if you pick a bad ordering of your rewrite rules. But I'd also note, when I first heard this, I was like, completion, I don't know if that's really a thing I'm interested in. Terminating, confluent, I don't really know. But there is another usage mode of completion, and that's the early stopping usage. And one way you can do that is in a goal-driven manner. If I have a goal equation I'm trying to prove, a left-hand side and a right-hand side term, I can run completion until the system is complete enough to prove the given goal equation. And then I don't necessarily need to get all the way to completing the entire system and getting the good rewrite rule system, which can be hard or impossible in general to actually get to the completed system. So that's a good usage case. And so it's a direct method for equational theorem proving, completion is. But also, you can use it in a simplification-driven manner. If you run a completion algorithm for a while, you'll get out a pile of rewrite rules, and maybe it won't be finished yet. It won't have gotten to the actual confluent terminating state. But these rewrite rules will be better in some sense than the ones you started with. And if you ran a term through those rules, you will get out a better simplified term, as good or better simplified term than the rules or equations you started with. So you don't need to run it all the way to the end. You don't need to run completion to completion. Okay, so how does completion work? The basic idea. So you have a set of equations you're taking in. Here, for example, I have x times 2, where x is a pattern variable that could match over terms. And this is going to be a rewrite rule, is equal to x shifted by 1. And then what I can do as a first step is I can orient it. I want to turn a bidirectional equation into a directed rewrite rule. And term order, again, is the idea that some terms are better than others, and that we want to more or less find lower cost terms. In the context in which I'm discussing it, that's kind of what you want to use your term order to do. So here we want x times 2 to be a higher in the term order than x left shifted by 1, because shifting by 1 is a better thing to do. In many cases, what you'll want to do is get the smaller term. In this case, they're the same size, but shifting is better than multiplying. Then what you do is you look at your rewrite system and you find places where there is a phase ordering problem, where there is a possible failure of confluence. So you find two left-hand sides that can overlap in a non-trivial way. And then when that happens, there is a term that could write this way or it could rewrite this way. And there's no guarantee that those things can rewrite back together again. So you can infer an equation that is a deduction of your equational system. And here, we said there's this phase ordering problem between turning multiplication by 2 into shifting by 1, or noticing x times y divided by y directly goes to x. And so if we have the overlap of those two things, we derive the equation that x left shifted by 1 divided by 2 is also the same thing as x. That is a true fact. And then we reduce the equations we've derived with respect to the rewrite rules. And that gives us a notion of simplification, or throwing out redundant equations that we didn't really need, that the rewrite rule system is already powerful enough to prove. And then you repeat. Okay, and so that's the basic thing. It's almost a brute force direct method to try and repair confluence. Now, there is a slightly more advanced form of completion where I didn't discuss anything where you could get at the beginning some rewrite rule that's a big hunkin' rewrite rule that's kind of ugly. Then later on, you turn your crank, and you end up with new rewrite rules that actually imply the old one, and it's junk now. But the system I presented earlier had no mechanism to delete or simplify amongst rewrite rules. It only derived new equations and simplified those equations. This R-simplify and L-simplify rule are a way of doing that, and it gives it a way to compact and sort of canonicalize your rewrite system itself. And this is from Bader and Nipkow, term rewriting and all that, a source of many of the ideas in these slides. So in particular, there are systems out there built that use completion. TRAAT is one of them. It's a theorem prover for equational logic. It's built around completion. It's written not naive, but optimized Haskell. It takes TP input, which is an automated reasoning format. And it does pretty good in the Cask unit equality proof division. So what we have here is these two rewrite rules written in the TP syntax. Multiplying x by 2 is the same as shifting x by 1. Dividing the multiplication of x times n, dividing by n is the same thing as x. And then I'm playing a little trick here on TRAAT, where it just so happens that if I give TRAAT an unprovable goal and it saturates, it will dump the resulting rewrite system. So I'm giving it true equals false, which it isn't going to be able to prove. And here I ran it, and it says ran out of critical pairs. Conjecture is not true, whatever. here's the final rewrite system. So this is the part to focus on right here. The multiplication times 2 is the same as shifting x by 1. Great, that was something we want to happen. Dividing multiplication of x times y divided by y is the same as x, also great. But now it's added in this new rule, which fixes the phase ordering or confluence problem. And so if you so happen to apply this first, now this rule can apply, and you'll still get to the best possible result for this system. Okay, so now that we've talked a bit about that, let's talk about how the union find can be seen as an instance of completion, in particular ground atomic completion. So before the rewrite rules had variables in them, like x, because they're things that are going to match patterns and rewrite. But now we're going to have atomic symbols, just sort of indivisible symbols, and they're going to be ground. So they're not really patterns. It's just things like A equals B, B equals C, C equals D. Okay, so why are we discussing this? Well, because an EGraph is roughly a union find plus a hash cons. So if we can understand the union find first, then we'll talk about the hash consiness next, or terminess next. So a union find is, I like to think of it as a forest of equivalence classes. And each tree in that forest is one of the equivalence classes. And the pointers in the tree point up to the parents, which is, less common when you're doing trees in programming or computers or data structures. Abstract syntax trees typically have pointers from the parents down to the children. But here we have pointers up to the parents. And what you do is, if you want to know if two things are in the same equivalence class, you chase the parent pointers up until they hit the root of the tree they're in. And if they hit the same root, then they're in the same equivalence class. If they hit two different roots, they're in different equivalence classes. And you can also incrementally make these things attach equivalence classes to each other by taking the root of one and pointing it up to the root of another tree. So we could also describe this find process, this find operation, which is finding the canonical root of an element, as a convergent dynamical system. If I had a set of nodes down here and I watched them as I was applied find, the sets would compress, they'd compress, until eventually I would just have the roots, things in the roots. But another way of saying a convergent dynamical system is a confluent terminating abstract rewrite system. An abstract rewrite system really is just saying there's a binary relation and I'm going to iterate it, which is a pretty general concept, and in particular discrete dynamical systems definitely fall into that. So here is the sort of table between the two. When I want to call find on a union find, that's the same thing as running the term rewrite system. When I want to call union on a union find, that is incrementally adding an equation to that completion system. I run completion, and then I have no equations in all rewrite rules, and I can throw one equation in there upon the call of union, run completion, and that'll turn it into a rewrite rule. The R and L simplify rules, which didn't discuss too much, but are for the interior simplification of rewrite rules, that dignifies the operation of path compression in a union find. In a union find, typically, as described in data structure course, as you're calling find, you can actually compress the tree while you're doing it to make it flatter. And the flatter the tree is, the faster calling find is. So it gets better and better as you call finds. But then here's an interesting distinction. The term ordering can be seen as the tie-breaking mechanism of a union find. So there are multiple ways of describing how to do union find, but when you call union, you find these roots, you decide which one's the parent of the other one. And the classic data structure way of doing that is you choose the tie-breaking such that you try and keep the thing flat, so the trees, the forest flat. So you need to track sort of depth or rank of these trees. But there are other reasons to tie break in different ways. You might have some intrinsic reason you think one node is better than another, or you might just want to tie break in a deterministic manner in order to avoid dependence on the order of assertions of unions. And that's more like the term ordering idea, where a priori we pick an ordering between our atoms. So we can also do this in Tree, and I have it. So Tree is a union find solver if we want to use it that way. So I can assert a pile of ground atomic equations, A equals B, B equals C, C equals D, D equals E, F equals G. And then I can run it through tree. And I get a resulting rewrite system down here. B rewrites to A, C rewrites to A, D rewrites to A, E rewrites to A. Those are all in the same equivalence class, and G rewrites to F. And I can diagram this thing. I can write these rewriting arrows as dotted red arrows. And we can see this is a forest, now with the roots down at the bottom, but a forest of two trees, and it's been completely flattened. It's in its canonical, most compressed form. And so that is a pictorial representation of a union-find data structure, and it corresponds directly to this rewriting rule system. I'll also note that Chui is a proof-producing union-find. Chui has some of the best proof production in terms of visuals and understanding that I've seen basically out of any automated theorem prover. So it will lead you line by line exactly what axioms dignify A equals B, B equals C, C equals D, A equals E. The query problem I gave it. I gave it an A equals E instead of true equals false. Pretty useful. And also you can use Chui as a proof-producing EGraph or other similar things. It's a pretty powerful system. Okay, so now moving one step further, we'll discuss how an EGraph is ground term completion, which is closer to what we actually care about. So an EGraph is a completed reduced ground rewrite system. And this sort of sense checks because an EGraph and ground completion are solving the same problem. A ground completion solves a pile of ground equalities, and an EGraph also solves a pile of ground equalities. So they're doing sort of the same thing. It kind of makes sense that these are related or identifiable. And here is sort of the code book of translating between the two worlds. We can associate the canonical term of a term rewrite system, a completed terminating confluent ground rewrite system. So you'd rewrite, and you'll eventually get to a canonical term of that. We can associate that with the E class. Think of them as sort of the same thing. The R and L simplify rules, again, dignify canonization of the EGraph. Running the rules, now this is more interesting, corresponds to extraction, the typical, most basic form of extraction from an EGraph. An EGraph in simplification solving mode, you want to extract a good term out of the EGraph once you're sick of doing rewriting. The typical thing you do is you want the simplest, most typical thing you can do is you want the smallest term in terms of node count. And there's a dynamic programming algorithm that can do that for the EGraph. But running the rewrite rules will get you the same thing if you make the association that the term order of the term rewriting system corresponds to the extraction objective of the EGraph. And also, in this case, if you use Knuth-Bendix ordering in particular, the weights there correspond exactly to the weights you can add to the extraction objective in the EGraph extraction algorithm. So now what we can do is we can take that pile of equations that I showed earlier, showing in the egg example. Here we have, grounded multiplication of A times 2 is equal to the shift of A by 1. We also discover this associativity rule, this division. Dividing 2 by 2 is the same thing as 1. Multiplying A times 1 is A. And then I can mark my starting term with a special big term that just sort of lets me keep track of it. And then I can run it through Chui and end up with this rewrite system. Okay, fine. And I can see that the starting term, the best thing in that equivalence class, is A. It did discover that the best thing to extract is A. And now here comes the most important slide of the talk. So I said that a crucial aspect of the uptake of EGraphs has been this graphical way of representing them. Here, this is the diagram from egg on the right of this canonized EGraph. But there is also, basically, I think, an equally compelling graphical representation of this grounded, reduced, confluent terminating ground rewrite system, for which I've copied exactly the output of Chui right here for reference. And so again, as in the union find, every arrow, rewriting arrow here, corresponds to one of these dotted red arrows. And we can see that there is a similarity here. Here's this division node. That's the same thing in some sense as this division node. multiplication node is this multiplication node, this A node is this A node. And we can see that these are all in the same E-class, they're in the same dotted line boundary, and these are all connected by red dotted arrows. But there are some crucial distinctions. Really, the eGraph is a lossy representation of this diagram. First off, the directionality of these arrows is not arbitrary. It's pointing from more complicated to simpler terms. So, if I had reversed this arrow, that'd be talking about something else. That'd be a different system, a different optimization objective. Second off, maybe more importantly, or equally importantly, I don't know, these are not e-nodes. These are terms. The children here point directly to other terms instead of to the indirection of the E-class. And the reason that I think this is important, both of these things are important, is that terms have a better notion of scope. And that has been a serious problem in the eGraph and extending it with new notions. This sort of clarifies and unentangles some issues that are in the eGraph while still keeping in a very interpretable, simple diagram. If you take anything away from this, this slide is the thing to take away, that a compressed ground rewrite system can be diagrammatically represented in an equally compelling way, and maybe in some senses a simpler way. There's less concepts involved than the eGraph diagram. Okay, so what if we wanted to bring the correspondence even closer to each other? Where are the E-classes and E-nodes? So what we can do is we can flatten. We can introduce fresh constants for every term, such that there are a term head is only applied to atoms. And then we make these things less than the term ordering, so the thing tends to will rewrite to these new fresh constants. So for example, if I had foo of biz, baz, bar equals bar, I would invent a new constant for bar, invent a new constant called E2 for baz. Biz of E2, which is this thing, is equal to a new constant. Foo of E3, E1 is equal to E4. And then finally, this asserting this equality is the same thing as saying E4 equals E1. And then I can, rewrite these things and orient them. And I want these things less in the term ordering, so it points to them. So if we look at this, we see that there are two kinds of rewrite rules here. There's ones that are from go from a term symbol applied to some number of E symbols, rewriting to an E symbol, and this directly corresponds to the E-node table saying which E-nodes belong in which E-class. And we can also notice some rewrite rules that were just E-class IDs to E-class IDs, and those correspond directly to the union find. Some observations. This is not obviously possible for scope terms. You can't just invent new constants, flat like atomic constants, and then transmit things that have come into scope, like into the deeper parts of the term. It just doesn't work. Maybe an approach to this is using something akin to slots, a presentation that was given at EGraphs 2024, where instead of having atomic E-class IDs, we have E-class IDs that can accept parameters of some kind. I'll also note this correspondence, I showed how eGraphs are a subcase of completion, but we can also look at this as completion is a generalization of eGraphs, where if you wanted an eGraph with universal for all variables or first class rules, completion is kind of that eGraph. Also, this connects back to a story that's been discussed a couple times at previous eGraph conferences and online in a couple papers about tree automata and their correspondence to eGraphs. So tree automata, my 10-cent summary of them, is that tree automata describes sets of trees by describing finite folds over those trees, which can fold to an accepting state or not. And so you can describe a finite state fold as what do you do when you have a cons constructor, for example, that receives Q1 and Q2 from the subfolds. And you can go to Q2 again, or Q3, or whatever. And that's a bottom-up tree automata. And we can see that if I rename Q to E, that corresponds it's very similar, very evocative of the things I was of this flattened form. It's all rewrite rules and equational reasoning and things. Okay, so then the other ingredient of E equality saturation is E-matching. You have an eGraph, but then you need to find patterns in it determine new equalities and assert them into the eGraph over and over and over again. That's the general methodology of equality saturation. And I'm not going to go into too deep in depth about how this works, but you can do it. You can directly e-match in the term rewriting form. And really, I think the intuition is that both the eGraph and this ground term rewriting system, in some sense, each e-class represents an infinite, possibly infinite number of terms. If you have a loopy eGraph, you could keep expanding the thing out, and finding more and more terms that correspond to that e-class. And what you do is you start at an e-class, you pick one of the e-nodes in there, and then you can go to those children, and then you have another e-class, and you can pick which of the many possible e-nodes there. And so there's a way of generating lazily, just eventually you'll ground out at some term occasionally, and then you'll just keep generating more and more terms. And so that's a way of generating a stream of terms out of it that occur in an e-class. But you can generate a stream of terms in a ground rewrite system quite simply, and that's by reversing the rewrite rules. If you want the funnel of terms that reduces to this canonical term, just take that term and then rewrite the rules right to left. And then I'll generate a bunch, and you can search for the terms you're looking for patterns in that thing. That's the most sort of brute force version of it. There are optimizations you can do on top of it. And in particular, there's top-down and bottom-up e-matching. And I wanted to make a few quick comments about bottom-up e-matching because I think it's really interesting, and I could deliver a whole talk, and maybe I will, about bottom e-matching. So it's the simplest e-matching algorithm. And here's how it works. You have a pattern, and it has a bunch of variables in there, a bunch of holes that you're going to seek inside the eGraph. What you can do is just completely guess each pattern variable. So you only have a finite number of e-classes in your eGraph, so to guess each of those is just a for loop over every e-class. And so if you have two pattern variables, for example, you have two nested for loops. And then once you have those variables grounded, you can just build the term by going upwards by the hashcons mechanism of the eGraph. You can just build the term corresponding to the pattern. And if it was something that was in the eGraph, oh great, you accept that pattern and you can rewrite it to the right-hand side. And if it wasn't in the eGraph, well, then that's not a matching pattern. So this plays nicer with theories, is the thing that's most exciting about that, in addition to being the simplest form of e-matching. And that's because when you come top down, you have things sort of semi-grounded. Things aren't like completely concrete yet. But when you're going up, you just make it as concrete as possible to start. And now you go up, go up, go up, go up, go up. And so, for example, if you had a permutation symmetric constructor of some kind, you can just sort the thing once you get up to it when you're building up the pattern. Whereas if you do top-down e-matching, you have to guess which of the permutations you need as you go down. So containers sort of become on the same level and easier to integrate. They sort of work the same way as e-nodes do. You just need the ability to build the thing given all of its subpieces instead of the ability to come from the top and guess stuff inside of it. And perhaps this is related to the eGraph, the acyclic eGraph. And perhaps bottom-up e-matching is better behaved in regards to polynomials and destructive rewrite rules, but that's ongoing work. So in e-matching, in distinction to completion we throw everything into a single sack, we just run it. But in equality saturation, we have a distinction of rules and the eGraph. And we don't have the rules smash against each other to make new inferences for reasons of performance, basically, or ability to sort of control the search a bit better. And this has a pre-existing similar thing in the automated reasoning community of strategies. So in resolution, there is this notion you can have incomplete but pragmatic limitations on resolution that guide the search in some more useful direction. In particular, what I'm referring to is something called the set of support strategy, where you have these active and passive rules, and the passive rules, I believe, aren't allowed to infer amongst themselves. They only allow an inference when it's active against active or active against passive. And the passive here would correspond to the equality saturation rules, and the active would correspond to the eGraph itself. But also note, interestingly, that prologue and datalog can be seen and historically kind of come from being incomplete strategies on resolution. And there is a chart one can make, an interesting chart, I think, of relating propositional theorem proving and equational theorem proving. And there's some boxes on here that I don't know what goes in that box, which is, you know, a methodology for generating ideas and projects. So resolution is very similar to paramodulation. Ordered resolution is like superposition. Not exactly sure what completion corresponds to in the propositional case. Maybe there's no good analog there. Ground ordered resolution is like the EGraph, which is like ground completion, which is like ground superposition. Prolog is like functional logic programming, and datalog is like egglog. And then what is the analog of answer set programming with deeply integrated equations, or lambda prolog with deep integration of equations, or hypothetical datalog, or a mini Cameron that operates equationally? I don't know. So now that we've discussed all of that, we can discuss a bit about how this perspective of completion guides away threads to pull on the problems of lambdas, context, and destructive rewriting. Things that have been very confusing how to approach in a principled way with the naive EGraph picture. So I'll note that today, actually, TRAAT already has a notion of a contextual EGraph, because TRAAT implements this paper, Efficient Encodings of First-Order Horn Formulas in Equational Logic. A horn formula is a single implication of these facts imply this fact, and there's a single fact in the head. And these are the sort of things that show up in datalog or prolog clauses. And TRAAT has it today, and they sort of do it by encoding it into an equational theory, which is very similar to the assume node technique in EGraphs from Sam Coward et al.'s work. Also note that ground superposition is, perhaps in some sense, a contextual EGraph. Ground superposition is kind of a generalization of completion, but it has clauses from the get-go. So here is a example superposition rule where S is equal to T and not U equals V or R, where R is some equation, let's say. If you rewrite that using the classical correspondence that not A or B is the same thing as A implies B, then it becomes the second form, which starts to look like a implication of a under the context of U equals V, we know R, then we can, you know, chew on that. So that's interesting. Also note that ground superposition is terminating but possibly explosive, being capable of encoding ground SAT solving, basically. Ground resolution is a possibly very explosive process, and ground superposition isn't much better. But maybe limitations, limiting the system in some way, might, or just not using the full capability of it, might still have good properties. There has been recent work on adding lambdas to superposition, and perhaps this technology can be applied to make a lambda EGraph. So both zipperposition, E, and Vampire, which are all automated first-order theorem provers, have gained support for higher-order reasoning fairly recently. And here's some papers to chew on. I don't completely understand these papers. I continue to read them every once in a while and try and figure out what ideas I can extract from them. But in some sense, if zipperposition or E or Vampires chose to offer the appropriate interface, they do probably have the appropriate algorithms to describe equality saturation within them. They need to be recombined, perhaps, in a non-trivial way, or many of their inference rules may need to be turned off in order to use it in this way. And finally, destructive rewriting. There is a notion that, like, you don't want to use equality saturation for obvious rewrite rules that are like, it's so obvious, I just need to take this rewrite rule. That's how people fail. Or perhaps the rewriting system already has excellent properties of confluence terminating. Can't you somehow abuse that to, like, cut down the search space of the EGraph and not use the general mechanisms for these rules that we already have a really good handle on? And I think there is a way of modeling this, perhaps, from the completion perspective as a combination problem question, which is in Chapter 9 of term rewriting and all that. And the question is, under what combination can you take two good rewrite systems and combine them and get a rewrite system that continues to have those good properties. And it's actually more subtle than you'd think. It happens less likely than you'd think that you can combine systems and they continue to have good properties. But in particular, the question is, under what conditions does completion of ground equations plus good rules stay well behaved? And I'll note that the term is, it's important perhaps to bring in these completion notions because the term ordering of the destructive rules probably informs how the ground completion should proceed. These orderings probably need to mesh with each other in some manner. So I've described how the union find and the eGraph can be seen as ground completion, clues to lambda context of destructive rewriting. And again, to reiterate, I think there's an interesting well to pump of how to take automated reasoning techniques and take them out of the theorem proving context and bring them into the compiler context, into the simplifier context. In addition, the eGraph, the ground case, is a very specialized form for which maybe these general systems like Chui or zipper position or E or vampire, maybe they're not tuned for, and maybe there's opportunity for very fast implementations like egg is shown, for this use case. So that's the talk. Thank you. I have an abstract here, which goes into a little more depth, describes these things slightly differently. And this is a sequence of blog posts in which I've discussed these ideas and some code and things to go along with it. In particular, for more general references on some of these concepts, term rewriting and all that, the Handbook of Automated Reasoning and Automated Reasoning Introduction Applications are good general references. Thank you for your time. I hope you enjoyed it.